Out in the frozen reaches of the solar system, Saturn could almost be a prototype of our Sun. The ringed gas giant and its swarm of moons provide clues to how entire star systems are formed. The shrouded moon Titan has an atmosphere like Earth's before life evolved. Saturn itself, 700 times the size of Earth, is mostly helium and hydrogen like the Sun. But it's still too small for gravity to ignite the nuclear fires that fuel the stars. Now, astronomers can detect the signs of such massive planets in orbit around other stars. Traces of more than 50 extrasolar planets have been detected since the first was discovered in 1995 by two Swiss astronomers. European astronomy programs based at observatories around the globe are part of the hunt for new worlds. In France, astronomers use a collection of optical telescopes to observe parts of our galaxy with the right conditions for stars and planets to form. Starlight from the telescopes is analysed by a spectrometer known as ELODI. ELODI can detect minute changes in the colour of a star's light that indicate a massive planet in orbit. But scientists want to find more than just huge gas giants. They want to find planets with roughly the same conditions as Earth. Astronomer Michael Blanc worked on the exploration of the Saturn system by the Cassini-Huygens spacecraft. Ground-based telescopes can detect the largest gas giants, but finding Earth-like planets will take different methods. Europe's space agency is preparing an array of space telescopes named Darwin to search for oxygen and carbon dioxide on certain extrasolar planets. Like its namesake Charles Darwin, it will be searching for the beginnings of life. This empty launch pad was supposed to be the prelude to a celebration. But when Japan's H-2A rocket had to be destroyed minutes after liftoff, it was the beginning of a witch hunt and a period of 18 months of soul-searching. The problem was eventually traced to a booster. Here, at the Japan Space Agency's launch site at Takanigoshima Space Center, a remote island about 1,200 kilometers southwest of Tokyo, engineers set out to examine every aspect of the H-2A's design. No easy task, with 300,000 individual parts. The result, they say, is a better rocket. Until its disastrous sixth mission, the H-2A had enjoyed 5 successful launches with payloads of satellites. The H-2A didn't just transport payloads into space, it carried Japan's reputation as a potential rival to US and European rockets in the commercial launching business. That reputation suffered a big dent. But the Japanese say that their space technology shouldn't be judged on this one failure, and like any industry, it's about experience. But success in the commercial satellite launching business isn't just about experience. It's also about reputation and money. There is no doubt that space is a growth business, with old satellites needing to be replaced and new customers emerging in Asia. To get back into contention for lucrative launch contracts, Japan must demonstrate that the H-2A is reliable and departs frequently for space. This is Skylab, a working laboratory developed by NASA to orbit the Earth, an endeavour that marked the transition from the exploration to exploitation of space. Skylab was 15 metres tall, 8 metres across, and had some 1,000 cubic metres of working space. Skylab was divided into a lower floor with crew quarters, wardroom, and medical experiment area, with the upper floor dedicated to space technology equipment. The multiple docking adapter provided docking ports for the command module, as well as housing the control console for the solar telescopes and a series of cameras for conducting Earth observations. The unmanned orbital workshop was launched in May 1973 atop a Saturn V rocket. But there were some problems early on. The temperature in Skylab rapidly rose because a meteorite shield had been ripped off during the launch. In addition, the lab's solar array panels had not been deployed. The launch of the first Skylab crew due the next day had to be postponed until solutions could be found. The urgent need was to stop the rapid temperature rise, which was achieved by reorientating the satellite so it was no longer broadside to the Sun. The next 10 days were hectic. Teams were immediately formed to find solutions to the problems. A major objective was to design and fabricate a thermal shield that could be deployed on the workshop to make Skylab habitable. Throughout the United States, teams worked round the clock in an all-out effort to perfect such a design. Meanwhile, at the Marshall Space Center in Alabama, crews were evaluating the installation of a parasol device in the Skylab underwater simulator. In conditions that approximated zero gravity, they also trained underwater in methods of freeing the jammed solar panels. But the actual work would have to wait on an eyewitness assessment by the astronauts in space. Time was becoming critical if Skylab was to be saved. Relief would come only from the thermal shield parasol, which would be deployed by the astronauts when they reached Skylab. Ten days after the initial launch, astronauts Conrad, Kerwin and Weiss were on their way to Skylab. It was the first step in the fulfillment of an opportunity to use men in space for practical humanistic benefits. After rendezvous with Skylab, a televised fly-around was performed to assess the damage. Most of the predictions were confirmed. The meteoroid shield had been ripped away, exposing the workshop's skin to the sun. One of the solar array panels had been completely torn off, and the other, only partially deployed, was jammed by a fragment of the damaged meteoroid shield. An unsuccessful attempt was made at freeing the panel before docking with the workshop. After a night's sleep aboard the command module, the astronauts entered the workshop and took steps at deploying the parasol. In mission control, optimism that the mission could be saved wasn't long coming, as Skylab's temperatures began dropping rapidly. The parasol was doing its job, but there was still a shortage of electrical power. The stuck solar wing had to be pulled out fully. But thanks to the work of the backup crew at Marshall, the procedures were worked out, freeing the solar panel. Astronauts Conrad and Kerwin went on their first spacewalk to repair the damage. This took 3.5 hours and was difficult work, but they prevailed and were able to sever the obstruction and pull out the panel. Within hours, the power situation was nearly normal. The mission could continue, transformed from near ruin to success. On Sunday, the 24th of April 2005, the Hubble Space Telescope, the most successful project in space science, celebrated its 15th anniversary in space. Hubble, a joint ESA and NASA project, revolutionized astronomy by looking deeper than ever before towards the beginning of space and time. It gave us stunning images that have had a lasting impact on people's interest in astronomy. Images that were better than even the biggest telescopes built on Earth could capture.
5, 4, 3.
It took 15 years to build Hubble, and then another 4 years of waiting before this ambitious space project was on the launch pad. In April 1990, 5 astronauts aboard the Space Shuttle Discovery deployed Hubble in an orbit roughly 600 kilometers above the Earth. But how great was their disappointment when shortly later it became obvious that Hubble's images were anything but sharp. Hubble's mirror had a serious flaw preventing it from taking sharp images. Its edge was too flat by a tiny fraction of the width of a human hair. Was this the end of the most sophisticated telescope in space before it had even started? Over the next 2 years, engineers and scientists from ESA and NASA worked tirelessly to develop and build a corrective optics package named COSTAR to correct Hubble's short-sightedness. In 1993, during the first Hubble servicing mission, COSTAR was fitted to Hubble in a series of breathtaking spacewalks. It succeeded on all accounts. The first images proved Hubble's glasses were working, and better than expected. This was not the first time the Space Shuttle visited Hubble. 3 more servicing missions followed, carried out by the Space Shuttle. But in 2005, it was cancelled after the tragic accident of Space Shuttle Columbia. Since then, NASA has decided that there would be no more Hubble servicing missions with the shuttle, which will focus on the completion of the International Space Station. Hubble was originally designed to operate for 15 years. But as long as its instruments work properly, it can continue its fruitful observations. But even when Hubble's unique mission eventually comes to an end, scientists say there are exciting plans ahead to ensure it will not mean the end of space astronomy. Space technology made it possible to surf on the internet with a wireless connection. Now a project from the European Space Agency is testing wireless technology on high-speed trains. The European Train Company, otherwise known as Red Trains, links Paris to several major European cities and is taking part in the ESA project by offering their travellers connection to the web during their journey. Aboard the Red Trains, commuters expect comfort and the speed, picturesque scenery, and the choice to relax or work during their high-speed journey across Europe. Thanks to space technology, these travellers can now access the internet with a wireless connection as well. The European Space Agency is testing the efficiency of users being able to connect to the web while travelling at very high speeds. They should be able to access all the resources offered on internet. The principle is simple. A satellite tracking antenna on the train's roof ensures a permanent link with a telecommunications satellite. The link is then relayed inside the train through wireless access points installed in the ceilings of the carriages. The success of this project would be a great technological achievement. It will create a continuous two-way link between a train travelling at 300 kilometers per hour and a satellite at an altitude of 36,000 kilometers. The project is being developed with ESA by the UK-based company 21net, an operator which specialises in providing internet access via satellite. Commuters can check emails, send messages, transfer documents, basically do everything you'd normally do at the office, getting the best out of broadband internet while the train races across Europe. Here is what scientists at NASA's Jet Propulsion Laboratory think they may have found. A massive asteroid belt containing 25 times more material than the one in our solar system. It circles a star 41 light years away. What interests the scientists is that it may give clues as to how rocky planets like our own Earth formed and where to look for them. The phenomenon was observed by the Spitzer telescope. Less well known than its orbiting fellow Hubble, Spitzer observes the universe in the infrared part of the spectrum. Spitzer looks for heat sources, and what it found orbiting star 69830 was excess radiation associated with a massive amount of rocky material. When dust and larger rocks jostle each other, they create friction and miniature explosions, which Spitzer picked up. Hubble's attention is also focused on the phenomenon. The system is too far away for Spitzer to actually generate an image. And this is what you might see on a hypothetical planet in the solar system that Spitzer observed. As the sun sets and the sky darkens, the asteroid belt is revealed as a brilliant band of light, sparkling as asteroids collide with each other. The Group on Earth observation brings together all spacefaring countries, and it's responsible for overseeing an ambitious 10-year plan to harmonise data gathered on the environment and security, both from satellites and such information that is gathered on the ground. Europe is at the forefront of this drive with its global monitoring for environment and security system known as GMES. GMES is a collaboration between the European Space Agency, who provide the satellite technology, and the European Commission, who harmonise and integrate the data. GMES is up and running, proving that the vision works and has very practical applications. Climate change is also affecting phenomena like forest fires, where a broad picture and harmonised data can help assess and even limit the damage. But it's not just Europe and its citizens that are able to benefit from GMES. GMES services are of great value to developing countries. The World Food Programme, that works in poor countries where infrastructure of information may not exist, can benefit from GMES. Nor is it just major phenomena that GMES observes. The system can, for example, observe land subsidence to within millimetres per year. This means that any city can look at these images and find out which parts are subsiding due to construction, due to pumping of groundwater, or due to extraction of natural gas or oil. GMES is a key element in the global Earth observation system of systems. The 10-year plan to harmonise all data gathered by every system on and around the Earth. And it points the way to much more effective monitoring of the environment and security of the entire Earth. GMES is Europe's contribution to that best scientific data. In August 2003, the planet Mars was at its closest to Earth since the dawn of history. Or certainly since the invention of the telescope. Astronomers said people viewing the planet managed to see a brilliant red star. Even a small telescope was able to show its disk and perhaps a few markings. Mars is certainly the favorite planet. Europe, Japan and the United States have all sent probes to it, and astronomers were excited as the planet approached to within 56 million kilometers of Earth, the closest, according to the experts, than at any time since the Ice Age, when mankind was hunting mammoths. Debate still continues on whether there has ever been life on the red planet, and it is certainly unlikely any discoveries will be made via the telescopes here on Earth. But the probes that circle Mars could be reporting back on the fundamental question which has fascinated people for thousands of years. In preparation for a spacewalk, astronauts train in simulated weightlessness in this, the world's largest swimming pool. Even as training continues, NASA had safety questions to answer before Discovery's flight. It is hard to determine how much damage the shuttle can safely handle. So far, it appears holes larger than 1/4 the width of a coin may be too large. And NASA is still developing techniques to come up with a reliable way to repair holes in the critical heat protection tiles and wing panels. It is testing everything from a silicone-based paste to a carbon-based patch. NASA took many precautions to prevent the kind of damage that doomed the shuttle Columbia, redesigning the external fuel tank to reduce the risk that a piece of insulating foam could fly off and punch a hole in the wing was one. NASA was under some pressure to get back into space with the shuttle missions, not only to complete the International Space Station, but also to prove that they can do it, that they can have a successful flight. NASA insisted, though, it would not fly unless it was certain the shuttle was ready. Saturn itself, 700 times the size of Earth, is mostly helium and hydrogen like the Sun. But it's still too small for gravity to ignite the nuclear fires that fuel the stars. Now, astronomers can detect the signs of such massive planets in orbit around other stars. Traces of more than 50 extrasolar planets have been detected since the first was discovered in 1995 by 2 Swiss astronomers. European astronomy programs based at observatories around the globe are part of the hunt for new worlds. In France, astronomers use a collection of optical telescopes to observe parts of our galaxy Out in the frozen reaches of the solar system, Saturn could almost be a prototype of our Sun. The ringed gas giant and its swarm of moons provide clues to how entire star systems are formed. The shrouded moon Titan has an atmosphere like Earth's before life evolved. Tokyo, engineers set out to examine every aspect of the H2A's design. No easy task, with 300,000 individual parts. The result, they say, is a better rocket. Until its disastrous sixth mission, the H2A had enjoyed 5 successful launches with payloads of satellites. The H2A didn't just transport payloads into space, it carried Japan's reputation as a potential rival to US and European rockets in the commercial launching business. That reputation suffered a big dent. But the Japanese say that their space technology shouldn't be judged on this one failure, and like any industry, it's about experience. But success in the commercial satellite launching business isn't just about experience. It's also with the right conditions for stars and planets to form. Starlight from the telescopes is analysed by a spectrometer known as ELODI. ELODI can detect minute changes in the colour of a star's light that indicate a massive planet in orbit. But scientists want to find more than just huge gas giants. They want to find planets with roughly the same conditions as Earth. Astronomer Michael Blanc worked on the exploration of the Saturn system by the Cassini-Huygens spacecraft. Ground-based telescopes can detect the largest gas giants, but finding Earth-like planets will take different methods. Europe's space agency is preparing an array of space telescopes named Darwin to search for oxygen and carbon dioxide on certain extrasolar planets. Like its namesake Charles Darwin, it will be searching for the beginnings of life. This empty launch pad was supposed to be the prelude to a celebration, but when Japan's H2A rocket had to be destroyed minutes after liftoff, it was the beginning of a witch hunt and a period of 18 months of soul-searching. The problem was eventually traced to a booster. Here, at the Japan Space Agency's launch site at Takanigoshima Space Center, a remote island about 1,200 kilometers southwest of